Section 1.6 is where we start to get into the math. We're not completely into the math at this point, but we do start to get into things like measurement and looking at ways to measure. Now, one of the first things we have to talk about are standard units. And the two main different units that we have are the System International, or SI, set of units, which typically uses the metric system. And the alternative set of units that we see a lot in the US would be the English system of units. And we actually have kind of a cautionary tale. We had a satellite that was sent to Mars a number of years back and built to a set of specifications, and it actually crashed right into the surface of Mars instead when it got there, wasting huge amounts of time and resources and effort. And the reason they determined after investigating this that this particular satellite crashed into the planet instead of orbiting it is that someone had made a set of measurements in English units, and the people they handed off their measurements and specifications to assumed that there were metric units used in that process because they weren't annotated or defined very carefully in the notes, and therefore they were off by a significant amount. And being off by a significant amount means you hit the surface instead of the atmosphere. So some base units that we're going to use. For length, we're going to use the metric system unit of the meter. That's the standard international standard set of units. For mass, we're going to look at the kilogram, which is abbreviated lowercase k and g. For time, the second is what we're all familiar with, so that's what we're using. For temperature, we're using the Kelvin. That's the standard temperature, although we also use degrees Celsius, or in the English system, degrees Fahrenheit, and we'll get into what those are. When we talk about amount of substance, so we're talking about a number of atoms or molecules, we're talking about a quantity that we refer to as the mole, and that abbreviation is MOL. I know, it always struck me as really odd that we're abbreviating a four-letter word in the first place, but then when we're abbreviating the four-letter word, we're using 3 letters. Would it really have been that hard just to go with the extra letter? Whatever. Anyway, electric current and luminous intensity, don't worry about it. We're not going to really be dealing with that, at least not in this chapter. So length. We just want you to get used to this. We're going to be doing more math related with this in terms of things like converting from one set of units to another later. But for right now, just get an idea. A yardstick, which is 3 feet, is a little bit shorter than a meter stick, which is 1 meter or 100 centimeters. Centimeters being cm is the abbreviation. The relationship between the English and the metric system units can be summed up in this relationship between centimeters and inches. We have about 2.54 centimeters equals to 1 inch. So a very tall person, a professional basketball player, is about 2 meters tall. I'm about 1.7 meters tall myself at about 6'3". A large building like the Empire State Building, notice this little discontinuous thing. This isn't to scale, between these two pictures. But Empire State Building is about 443 meters tall, so over 1,000 feet, well over 1,000 feet tall. Now, mass, we actually refer back to, or at least used to refer back to, this very specific object held carefully within a vacuum to keep it from decaying or becoming oxidized or rusted in any way. And that particular object weighed exactly 1 kilogram. Okay? Now, in terms of the conversion to English units, a kilogram is about a fifth more than 2 pounds, so about 2.2 pounds. Or if you're thinking of those boxes of butter, think about 2 of those boxes of butter and almost 1 more stick of the 4 sticks of butter. As a comparison, a nickel weighs about 5 grams. A kilogram, by the way, is 1,000 grams. That's what kilo means, 1,000, and we'll get into that a little bit more later. 1 kilogram. And this kitten right here is about half a kilogram worth of cute or so right there. Time is actually looked at and measured and kept track of by an atomic clock at this point. The atomic clock looks at nuclear decay of a particular isotope of cesium, and that nuclear decay happens at a very regular interval, so it's this process of the breakup of certain types of atoms of an element cesium, and this is all done in some very futuristic, high-tech, almost alien-looking devices, but they allow for keeping a very accurate time. In fact, right now, it used to be you would have to call a phone number, and that phone number would give you the time to the nearest second and register that time with the atomic clock somewhere else in the world so that everyone could be on the same time. Now everybody just basically looks at their cell phone, which is synchronized with towers, which is synchronized to the atomic clock as well. There's an interesting little article as well online that you can look at about how using global positioning requires very accurate measurements of time. So we're actually looking at ways to measure the second to hundreds and thousands and 10,000ths of a decimal point of a second in terms of precision. Now temperature is a little bit dicier. We have a whole formula that goes into temperature, and what we have in terms of Fahrenheit versus Celsius versus Kelvin is a little bit of a difference between the temperatures of when water boils, water freezes, and absolute zero, which is as cold as you can actually get in any measurable way. So for Celsius, we have a nice even temperature distribution. 100 degrees Celsius is where water boils, 0 degrees Celsius is where water freezes, and I got about 100-degree difference between. For Kelvin temperature, which is the international system, all we do is we move down to the coldest temperature possible, and we call that 0. And then on that scale, with the degrees being exactly the same size as each other, meaning 100 of them between freezing and boiling of water, we get water to freeze at about 273 Kelvin degrees. It's about 273.15. So if you want the Kelvin temperature, all you have to do is add that 273.15 to whatever the Celsius temperature is. So if the Celsius temperature is 0, the Kelvin temperature is about 273. If the Celsius temperature is 100, 100 plus 273 gives us the Kelvin temperature of 373. Now, unfortunately, the Fahrenheit system is not quite aligned with the Celsius system and vice versa. So we actually run into some problems in terms of understanding how to interconvert between the two systems. For one thing, water freezes in this system at 32 degrees Fahrenheit and boils at 212. Well, that gives us 180 Fahrenheit degrees between those two extremes. So that means we do not have the same size of degree. A Celsius degree is actually a little bit larger than a Fahrenheit degree. We need more Fahrenheit degrees to equal a smaller number of Celsius ones. So because of that, and because of this offset of 32 degrees between the 0 points of these two systems, we actually have a fairly complicated formula to calculate differences between the two systems. So let's try that. We have 10 degrees Celsius, so that's kind of a slightly chilly day. What is that in Fahrenheit? Well, our formula tells us that we convert the degrees Celsius by multiplying by this ratio of there are 9 degrees Fahrenheit for every 5 degrees Celsius. Okay. Notice that if I multiply by this fraction, I get 90 and then divide by 5, and degrees Celsius divided by degrees Celsius means those degrees Celsius cancel out. So we have 90 over 5. Let me pull out a calculator and actually do that, because I'm not doing that in my head right now for some reason. Let's see, calculator, 90 divided by 5, 18. Yeah, I really probably should have been able to do that in my head, but oh well. So 18 degrees Fahrenheit. but we have to remember that we're offset. 0 Celsius is 32 degrees offset. So now we have to add that 32 degrees back in, and 10 degrees Celsius therefore comes out to be 50 degrees Fahrenheit. Okay? So go ahead and try room temperature. Pause the video, see if you start with 22 degrees Celsius, what you end up with in terms of Fahrenheit. Okay, so you've paused it, you've tried it, you've come back. Same procedure. We have 22 times 9. Punch that into the calculator. I'm definitely not doing that in my head. We get 39.6 degrees Fahrenheit. Celsius canceling out. And we add the 32 back into that. And we get 71.6 degrees. Yeah, about room temperature. Excellent. Well, we can do this the same way. What about the... why did I lose? There we go. If we have 98.6 degrees on the thermometer, human body temperature, what is that in Celsius? Now, we're in Fahrenheit already, so that 32 degrees Fahrenheit that we have to shift by has to happen now before we turn it into Celsius. So 98.6, subtract off 32 degrees Fahrenheit right away, and we get 98.6 minus 32, bing, 66.6 degrees Fahrenheit. Now we are going to take that 66.6 degrees Fahrenheit and multiply it by 5 degrees Celsius for every 9 degrees Fahrenheit, and that's the ratio. All this basically is 100 Celsius degrees for every 180 Fahrenheit degrees. Right? That was our number of degrees between boiling and freezing. So that's our conversion factor for this particular set of units. Okay, so when we do this, times 5 divided by 9, we get 37.0 degrees Celsius. Okay? So 37.0 degrees Celsius is body temperature, but in Celsius degrees. No big deal. Well, if you cook a pizza in a brick oven, you have about 425 degrees Fahrenheit. Pause it again, calculate it through, tell me what the actual temperature is there for degrees Celsius for the perfect temperature to cook a brick oven pizza at. Okay, so you're back. So what we want to do right off the bat, hopefully what you did is you subtracted 32, and you got 393 Fahrenheit. Now we're going to take that 393 Fahrenheit and multiply by 5 over 9. And we get about 218 degrees Celsius, rounding to about 3 digits here and ignoring that 0.33333333. So there we go, no big deal. Kelvin is just as easy. If we have helium at 4.2 degrees Kelvin, and that's where helium gas turns into a liquid, how do we get this into degrees Celsius? Well, degrees Celsius are just a different 0 point compared to Kelvin. Okay, so all we have to do is subtract if Kelvin equals the degrees Celsius plus 273.14, is it 14 or 15? 15. Then degrees Celsius, if we rearrange this, is Kelvin minus 273.15. So we have 4.2 Kelvin minus 273.15, and we get 268.95 negative. We're not going to get into rounding this at the moment. This is degrees Celsius now. But know that that's the approximate temperature that you get here, just by converting from Kelvin to degrees Celsius. Note we can have negative temperatures in Fahrenheit, we can have negative temperatures in Celsius, and in fact, for fun at some point, turn negative 40 Celsius into Fahrenheit. See what you get. It's kind of entertaining. But in Kelvin, however, you cannot have a negative temperature because the coldest you can get is defined as 0 Kelvin already. We also want you to know prefixes, and I'm only going to hold you accountable to tera through femto. So you need to memorize all of these prefixes, which are just multipliers on numbers. So for instance, when I said a kilogram, that means that what I'm talking about is 1,000 times bigger than the original base unit. So a kilogram is just 1,000 times bigger than the base unit that the kilo follows. So 1,000 times 1 gram, or 1,000 grams. Okay? A centa is just 0.01 of a whatever it is that follows it. So 1 centimeter, if we were looking at the centa, that means it is 0.01 of whatever follows after it, which is meter. So it is 0.01 of a meter. That's what centa means. Okay? So we want you to know tera through femto, and you have to memorize the symbol, like small lowercase k for kilo, lowercase c for centa, uppercase G for giga, and you have to know what the multiplier is so that you can use it when you're describing large or small numbers. And so let's practice this. So what's a better way to represent this particular scientific notation quantity? All right, well, 5.57 times 10 to the negative fifth is in scientific notation. It's actually this number. Right? So it's got all these zeros and that sort of thing. But if we look back at the previous chart, what's closest to times 10 to the negative fifth? Probably this one, micro. So it's a little bit bigger than micro. So that means what we can do is we can take this into times 10 to the negative sixth. So 55.7 times 10 to the negative sixth meters. And then we can take this times 10 to the negative sixth part of scientific notation and say 55.7 micro, which is this little Greek symbol. It looks like a U with a big tail, meters. Alright? So let's look at this as well now in the second example. How do we represent this quantity? Go ahead and take a second, pause it, look up the chart if you haven't memorized it yet. Right, so we come back. The closest thing to 10 to the 7th grams would be about 10 to the 6th grams on our chart, which is mega. So if we have this 10 to the 6th instead of 7th, what we're looking at is something that's actually a little bit bigger than 10 to the negative 6. It's 10 times bigger. So that means we have 32 times 10 to the 6th grams. So when we turn it into megagrams, 10 to the negative 6 represented by the m, we have 32 megagrams. grams. Huh? Excellent. We also have something called derived units. These are units that we get from multiplying or dividing standard units by each other. So for instance, volume is a derived unit from length, so from the meter or from the centimeter. If I have something that's 10 centimeters by 10 centimeters by 10 centimeters, I can calculate the volume of that particular object, and that would be 1,000 centimeters cubed, or cubic centimeters. Centimeters times centimeters times centimeters is centimeters times itself 3 times, so that's where the cubed comes in, plus 10 times 10 times 10 is equal to 1,000. Alright, so this derived unit is a unit of volume. The cubic centimeter, by the way, cubic centimeters, are also synonymous with the milliliter. So milliliter is 1,000th of a liter. So 1,000 of those milliliters would be a liter. So this little box right here actually represents 1 liter worth of volume. So half of a 2-liter soda bottle. Density is another derived unit. Density is just the amount of substance present divided by the volume that that substance takes up. So when we have this as a derived unit, we're going to get units of things like, say, grams per milliliter. And that's a mass, grams, and a volume, milliliters. But the overall unit for density is this ratio. And density you can kind of think of as the amount of stuff crammed into a certain amount of space. The age-old riddle is always, which weighs more, a pound of lead or a pound of feathers? Well, of course, a pound is a pound. They basically weigh the exact same thing, but what you're thinking of in your head when you think of that is a pound of feathers is going to be a huge amount of feathers. It's going to take a lot to get a pound of feathers. But a pound of lead, you need a very small volume of in order to equal that much substance, that much mass of substance. And so while they may occupy different sizes, feathers being much less dense, meaning less mass for every unit of volume than lead is, they both actually have the same amount of mass. So if we're going to calculate density, what we're going to be looking at is, in this particular problem, is an object with a mass of 22.5 grams and a volume of 2.38 centimeters, which is a volume measurement. So if we take this particular set of units and we put them into the form that density is here, where we have grams over centimeters, or mass over volume, all we have to do is punch that into a calculator, and we get the numerical value of 9.45, and the units are these combined units of density, which is mass over volume, grams per centimeter. We can also look at this qualitative example where we're talking about the heating of a substance such as copper, and the density of that substance will decrease as the sample is heated up. And this is similar for most objects. Most objects lose their density, not lose their density, but have a decrease in density as the particular sample, copper in this case, is heated up. So we can say about this, which the following things are true. When we go from room temperature, it's 95 degrees Celsius. So we have this lump of copper. We're going to go from heating it, we're going to heat it from room temperature all the way up to 95 degrees Celsius. When that happens, which one of those statements is correct? Well, can it be lighter? Well, no, because we said before a pound of feathers is a pound of lead. These things aren't becoming heavier or having more mass. It's the same chunk of object that we started with. Instead, all we're doing is doing something else, but we're not taking away any of the mass to it. Well, likewise, we're also not adding any mass to it. It's not becoming any heavier either. So if something isn't getting any heavier and isn't getting any lighter, and the ratio that's decreasing is the mass to volume ratio, what has to change instead to make that ratio smaller? The mass, circling here, has to stay constant. So that means that in reality the volume must be going up. If we look at some simple fractions, we can see how that could be the case. If the 1 and 1/3 stays constant, but the overall fraction has to drop, we keep the 1. The only way to make that fraction into a smaller fraction is by increasing the bottom number, which in this case is the volume. So expanding volume means a lowering density.